So far in this series, we've shown how the only route to fusion energy that produces capital costs much lower than existing energy sources is devices that use internal magnetic fields only and hydrogen boron fuel. So in this episode, we're going to look at the three devices that can produce those combinations of conditions, which is lasers, Z-pinch, and the device we work with, the dense plasma focus. So let's start with the lasers. So in this approach, the lasers aren't used directly to heat the target in the plasma. They're used indirectly to produce a beam of protons that then produces the fusion. So let's see how that's done. It's actually pretty clever. This is an idea that was developed in the 1970s by laser pioneer John Dawson, and then was implemented with very powerful lasers starting at the beginning of this present 21st century.
Tired of inflation, wars, and inequality caused by the energy crisis? LPPFusion is developing a solution that could allow everyone to have cheap, clean, off-grid, and sustainable fusion energy. Invest now as we seek to bring this potentially life-changing technology to market.
What happens is you take a laser that can emit light in a fraction of a trillionth of a second, and you focus that on a thin film target, which is called the pitcher. That's pitcher as in baseball, not as in the kitchen. When this extremely intense beam of light hits the thin film target, you suddenly produce a ball of very hot plasma expanding outward. Now, the electrons being lighter, they move away from the laser beam much faster than the ions. So the ions see a huge electric field produced by the fact that the electrons are way ahead of them. So they start accelerating because of this electric field to catch up with the electrons. So that's what produces the beam. And the beam focuses itself partially through the electric fields and partially through the very powerful magnetic fields that the current in the beam create. That beam then smashes into a second target, which has boron in it. That's the catcher. So the beam of protons starts to interact with the boron ions in the second target, and that produces the fusion reactions. Ideally, you get enough fusion reactions, and that produces the fusion reactions. Ideally, you get enough fusion reactions so that you create a burn front where the fusion reactions are heating up the rest of the target to fusion temperatures and then producing more and more fusion. So the aim is to produce this burn front that burns through most of the target before it has time to expand. And the expansion of the target is being held back by the pinch effect generated by the beam itself. Now, this approach has two big advantages. One is you start with solid density material. So the plasma is solid density, high density from the very start. Second of all, you can use the initial experiments powerful laser facilities that have already been set up, that already exist in universities and big government labs. So that's why HB11, which is the company that initiated this approach, and Marvel Fusion in Germany have gotten a leg up because they've started doing experiments with these existing lasers. And that's true of not only these companies, but several big government and university labs that are starting to do their own experiments. But this has a big disadvantage. it's a very inefficient way of getting energy into the target. Lasers of this sort are typically only about 1% efficient. And the conversion of the laser energy into the beam energy is maybe 10% efficient. So you're getting a very small fraction of the energy into the target. So that means you have to get hundreds of times more fusion energy out of the target than you put into it. Now that is possible because if you get a burn front, the bigger the target, the more fusion energy you can get out of it. So it's not a showstopper, but it is a big disadvantage. So with this approach, what you end up aiming for is medium-sized generators where the big part of the cost is the lasers themselves and their capacitor banks. So you've got maybe $200 or $300 or $400 million investment per generator plant. But you can potentially get gigawatts of energy out. So this device does still have a chance of reaching capital costs that are much less than the dollar per watt that existing energy sources have. So the second approach is called a Z-pinch. Now, a Z-pinch is a relative of our device, the dense plasma focus, but it's even simpler in conception. In a Z-pinch, you simply put a large current into a linear conductor, and that produces a plasma where the current simply pinches itself together along the line of the plasma. So this is an example of a very tiny Z-pinch device. So you see the plasma contracting perpendicular to its length. The problem with this approach is that you only have contraction in two directions. You don't have contraction along the length. So that means even huge machines like the Z machine, which is hundreds of times more powerful than our FF2B, reaches densities only about 1/1000th the density of air. Our FF2B, with much less power, has already reached densities about 1/3 that of air. Now, that's not where we need to be, which is almost 1,000 times the density of air, almost solid density. But it's a lot more than the much bigger Z machine. And that's because we can compress in three directions, not just two. So again, this is a possible route, but it does involve bigger machines, more powerful machines to get to the same density. So leaving the best to last is the dense plasma focus that we use. Advantage of the dense plasma focus is we start with electricity and we keep the energy in the form of electricity all the way through. So we can have a very efficient transfer of energy into the plasma. Now, the way this works, and we've described this in detail in other videos, is that we use a series of instabilities, all using the pinch effect to compress and heat the plasma by stages. So we start out with an array of evenly spaced current filaments. Again, they're pinched together by their own currents. They fountain into the center of the anode, producing a single filament, which then kinks up into the tiny plasmoid. Again, the plasmoid shrinks in all three directions, producing very high densities and very high magnetic fields. Thousands of Teslas, as we've already achieved. So this heats up to fusion temperatures, produces the fusion reactions, and then the energy is exhausted mainly in the form of an ion beam that's generated by the decay of the magnetic fields within the plasmoid. So since this is a very economical machine, we built our device, including all the diagnostic instruments, for only $500,000. We can do experiments much more cheaply than with any other approach. And together with the fact that we can achieve capital costs that are way below that of existing energy sources, that's why we think that this is the fastest route to fusion energy. And it's not just that we think it. We have published these results in peer-reviewed journals, reviewed by researchers at our competitors, and they haven't raised any objections. So that's the summary. And in the next episode, we'll look at what are the results. Right now, who is leading in the fusion race and by what measures in actual scientific results. Tired of inflation, wars, and inequality caused by the energy crisis? LPPFusion is developing a solution that could allow everyone to have cheap, clean, off-grid, and sustainable fusion energy. Invest now as we seek to bring this potentially life-changing technology to market. For more information, visit lppfusion.com.